Thank you very much. Thank you very much. It's a real pleasure to be here. It's an honor to be part of this very lovely, informative workshop. So just to give you an idea, maybe I'm not using the right terminology about what enumerative geometry is. Let me just give you some very simple classical questions that kind of go into the story. So here's a question. So you take x, I mean, we know the answer. So you take x of hypersurface of degree d inside a projective space. So it's dimension n, and let's say that d is equal to 2n minus 1. Then it's known there are, so smooth, let's say it's smooth hypersurface. So in other words, dimension of x is equal to n. D is degree. Then there are finitely many lines. L lying inside of x. Question is how many? Okay. So let's see. Is this right? If n is 1, yeah, then it's a line. So then the answer is 1. That's easy. So what about, for example, n equals 2? That's the dimension. That's the famous 27 lines on a cubic surface. Okay, goes way back to the 19th century. Great study of that. Okay, another question might be, take C inside of P2, smooth curve. I mean, these are all elementary questions, nothing fancy, of degree D. What is the genus? Or, let's see, maybe here's a more, maybe another fun one. You take 5 lines. This is in P2 in general position. How many conics? So smooth conics, conic curves are tangent to all 5 lines. Okay, so these problems all have a similar setup in that they're asking for a number in their answer. Okay, the answer is a number, and you solve these sort of a 3-step process. The first step is you translate to forming either an intersection product or some characteristic class on some, usually, let's say, smooth projective variety. And then, so you get some class, so a cohomology class or a class in a Chow ring, and then you apply either a push-forward map or, depending on your preference of taste, push forward, or trace map to get out of this a number. And then you have to interpret the number. Then you interpret the number. Or possibly even reinterpret the number. So in this case, so here the number was 27, and here the genus is, d minus 1, d minus 2 over 2. And in this case, the answer is, depending on who you ask, it's either 32 or 1. So, this is the fun one. It's actually, this is the right answer. This is the wrong answer, but this is the answer you get if you do these two, in the stupid way. Because the point is, each one of these. So the condition that C is tangent to a line L defines a quadric QL inside of P5. Okay, and then you intersect 5 quadrics in P5, and so that's the first part, and then you intersect them, and you use the fact that you know Zoo's theorem. That's the intersection theory in projective space, to say, well, this is degree 2, so you have 2 to the 5th intersections. That's the 32, and then you realize that that's wrong because there are a lot, because we said smooth conics, and for example, if you take any other line, if L is any other line, and you just take twice L, in other words, take the linear equation and its square, that'll be tangent to anything from the definition of tangency. In other words, it'll solve this equation. And so you get all the lines in P2, in other words, the entire what do you call it, Veronese embedding of P2 inside of P5 lies inside the intersection, and you then have to count how many of those 32 points lie inside their surface, and there are actually 31 of them lying there, and one of them lies there. Okay, anyways, just I'm saying it's, sometimes you get a number and it's not the number you want. Good, so that's all very classical, and then there are more modern versions of this where things like counting the number of rational curves on a smooth cubic hypersurface in, rather quintic hypersurface in P3, and then you can grade by degree, you get a generating function, and this is one of the starts in Gromov-Witten theory. And that's also sort of in this fashion. So what we want to do here is try to refine the answers, try to get answers in quadratic forms rather than in integers. Okay, so that's the idea. Okay. And so what we'll do, give 4 lectures. So today I'll talk about some of the, more about the background of how you do this. So this involves things like the so-called Milnor-Witt K groups or K sheaves, and things like Chow-Witt groups. So as you'll see today, these are all in some sense refinements. This is a sort of a, if you might call it a quadratic refinement of the Milner K groups of a field. I'll explain what those are. And these are quadratic refinements of the Chow groups of cycles mod rational equivalence. And then talk about their relation, how these fit to motivic stable homotopy theory, SH of K. Okay, so that this is sort of very concrete, and this is very abstract, and it's actually nice to have both points of view to work with these things. That's why we'll do both of them. And then, so lecture 2, then we'll start using these things. We'll apply this to give quadratic refinements. So the genus is essentially telling you what the Euler characteristic of that curve is, so refinements of Euler characteristics. And when you want to compute Euler characteristics for curves, you have the Riemann-Hurwicz formula. So There's also a quadratic refinement of this. Okay. The next lecture will be about how you can form quadratic refinements of more modern things. So in Gromov-Witten theory, so this will be quadratic refinements of so-called virtual fundamental classes. And then the last lecture, okay, this will be more about the characteristic class story. So in this first problem, the way you solve this is you view your defining equation as giving you a section of the dth symmetric power of the rank 2 bundle on the Grassmanni and of two planes in some space. And then you want to find out how many zeros that has, and that's given by a top Chern class, so you need to know how to calculate what this top Chern class is. So this is sort of, will be a quadratic version of the usual calculus of Chern classes. So there's a nice theory developed by Alexei Anievsky and other people, Panin, Walters, leading to a theory of what are called Pontryagin classes, and those are an analog, an algebraic analog of the classical Pontryagin classes of a real bundle. And so you can actually work with those things in the same way you work with Chern classes. Working with Chern classes is just playing with symmetric functions, and there's a similar story for these classes, but you have to do a few things. Okay, so that's the program. Any questions? Okay, a little early for questions, I guess. So. Good. Okay, so let's get started. First I want to, a little history. This will be Bloch's formula and the Milner K sheaves. Okay, so we all know what K theory is now, right? And you can form, so let's take X to be a smooth variety over some field K, and then we can take U inside of X, some open, and send it to the pth K groups of U. This is the algebraic K groups. This is a pre-sheaf, and this gives rise to the associated Zariski sheaf Kp. And so, one of the theorems of Quillen from his algebraic K theory 1 was that there's a natural isomorphism of the pth cohomology on X of this K sheaf with Chow-P of X. So, and what's this? This is just equal to the algebraic cycles of codimension P mod rational equivalence. So let's write it this way. It's the direct sum over all points of codimension P. So I'll use this notation for the codimension P points on X of Z. This is just the free abelian group on the codimension P subvarieties, modulo, so divisors of functions. So I'll just say image under some divisor map from, well, you can do the same thing. You can take the sum over things of one higher dimension, so one less codimension of the function field going to this direct sum here. So this is the relation of rational equivalence. Okay. Good, and the idea was he used so-called Gersten complex, Gersten resolution of this sheaf. So I'm not going to say what this is, there's a resolution of this thing by sheaves, and the last two terms, the last term is essentially when you take the global sections, you get this. The next to the last term gives you this, and the resolution by Flask sheaves, and so this gives you the Pieth cohomology. It's exactly this. Okay, so for our purposes, K-theory is, of course, as we've seen, is a pretty complicated beast. So I think it was Kato around in the 80s gave, in some sense, more elementary description of this story. Just using the Milner K groups defined by Milner back in the early, around 1970, I guess. Okay, so So let's see if I get my notation right. So Kato used Milner's K groups to give an analogous description. So let me remind you just what are the Milner K groups. So let's let F be a field. And then you define this graded ring. So graded, say, Z algebra with generators. Just write them so as a symbol, U in degree 1. This is for U, a unit, non-zero element in the field. And relations as follows. Well, let's see. Let me just first give the funny one. You have the Steinberg relation. That if you multiply u with 1 minus u, you get 0. And this is, of course, both have to make sense. For u has to be not equal to 0 or 1 in the field. And the second one is that this symbol is additive with respect to multiplication. So, in other words, okay, good. So then we often write the product, so we write for this thing, so-called symbol, N symbol. Okay, now we want to make this into a sheaf, so you need some kind of boundary map. So for O, a discrete valuation ring with quotient field F, residue field K, and let's say we choose a parameter T to give the maximal ideal, then we can define, there's a, well, I'm not going to define it, there is, let me put it this way, there is a well-defined map from Milner Kn of F to Milner Kn minus 1 of the residue field, which is just characterized by the property that if you have units, if you have n units, this is 0. And if you take the boundary of T against a bunch of units, this is just equal to the residue of the units modulo the maximal ideal. Okay, so turns out that this thing, the relations will tell you that you can generate everything in the field by things like this. So that gives you a good definition. Maybe I just call that delta O. Depends on the O. And now, so you can make the unramified sheaf. So you define this Milner K sheaf. So on a smooth variety X as the so-called unramified sheaf associated to this structure. In other words, you take the coproduct in the category of sheaves of overall codimension 0 points, so of the Milner Kn of the residue field. So if X is irreducible, this just means you take the Milner Kn of the function field of X, and then you have a bunch of maps. So you have sort of a bunch collection of, let me call them delta Yx, going to, I should take Ix lower star to view it as a sheaf. And then you have, so the Y codimension 1 points, Iy lower star of Milner Kn minus 1 of Ky. And what this delta xy is, delta yx, I guess, is if y happens to lie in the component, the closure of this generic point x, then we have O. We can take the local ring on this component at the point y, and then delta yx is just delta O. And if y is not in this closure, then you set this delta yx to be 0. Okay, and then so you have this gadget, and you just take, you define this sheaf to just be the kernel of this map. So it's the things in the function field which at every codimension 1 point have trivial, so tame symbol, this thing is called. Okay, so that's what that is. And this is actually the start of a beautiful resolution. So, right. Okay, so, all right, so this continues. I mean, once you see how to do it from codimension 0 to codimension 1, you can do the same thing. So you have this sheaf here. By definition, it goes into the this boundary map, which is just the collection of these things, continues on. So in the ith or jth stage, it looks like this, maybe p stage. So ix lower star, Milner Kn minus p, kx, continues on until you can't go anymore. And so right, so this is the stage where it starts to look familiar. So here you have 1 of kx, and you have this boundary map. Okay, and then it stops because, well, the generators in this Milner K theory are all in non-negative degree. They're all in degree 1, so there's nothing in negative degree. Can't go any further down. And of course, since the generators were in degree 1 and it's an algebra, and the relations are all homogeneous, right? So this thing is just z. There's nothing else here. And again, the relations were all just saying that this symbol was multiplicative, sends multiplication to addition, and there are no higher relations in degree 1, right, than the other Steinberg relations degree 2. So this thing is just equal to this guy here, and this thing here is just equal to the divisor map that I wrote down before. So when you take, so if you apply global sections and take HP, these are all flask sheaves because any sheaf of this form on a scheme is flask, and take HP, you get HP on X, Milner Kp of X is isomorphic to the co-kernel here, which is Chow-P. So I guess this is due to Kato. Okay, so I think that explained that. So now, now we give the quadratic refinement. This is the, that was all by way of background. Milnor-Witt sheaves. This is really what we want to talk about. So again, this was, yeah, it's a funny history. We're going to do it in reverse. It really started out, the story started out with the work of Hoplins-Morel, and then this was looked at by Fazel, and they defined what are now called Chow-Witt groups. And there's an extra Chow-Witt groups. And then later on, Hopkins and Morel, so then Hopkins-Morel defined so-called Milnor-Witt sheaves, or yeah, Milnor-Witt. And also with a twisted version, L here is a line bundle. So you think of it as an orientation. And there's the formula, these, so you, turns out almost a definition. This will turn out to be HP on X of Milnor-Witt P of L. Turns out. Let's say even a definition, or it's a theorem, I don't know, any way to put it. Okay, so let's discuss this. So first of all, let's again let F be a field. And you define this guy here is the graded Z algebra with generators. So first of all, you have in degree 1, you have a symbol U for U, a unit. So it looks very similar, but then you have another one to make life difficult. You have something in degree -1, just called eta. There's only one extra generator in degree -1, and it's sort of a universal generator. It doesn't have anything to do directly with the field. And now what about the relations? You're going to have room? Yeah, I think I'll have room. Relations. Okay. So let's have a relation 0. Relation 0 is just that this new generator commutes with the old generators. Okay, and then we have relation 1, Steinberg relation, same as before. And what about relation 2? That was the additivity. So this becomes different. This is some funny business. If you take the symbol associated to a product, it's equal to the sum of the symbols plus an error term. So notice this is a homogeneous relation of degree 1 because this has degree -1, this is degree 2. So it's homogeneous at least. And then you have a third relation which looks completely bizarre first time you see this. So what you do is you let H be the following element in degree 0, note, you take 1, right, we have a 1 in here because it's a Z algebra, plus eta times, oh, but you don't take 1. Sorry. You take 2 plus eta times minus 1. Okay, then eta times h equals 0. Okay, that's the last relation. Okay. So now you want to, again, extend this to a sheaf. And the strategy is exactly the same as for Milner K theory. Right, you define some kind of symbol map that lowers the degree. And then make the unramified sheaf with respect to that symbol map. Okay. Is that what I want to say? Yeah, I guess that's what I want to say. Okay. So now you do the same thing. You start with O, dVr. Quotient field of O is F. Residue field of O is K. You choose a parameter. The maximal ideal is generated by T. And then we define, well, let's say there is a map. I won't define a map, but I'm going to put this in the notation. It depends on the T, the choice of parameter. That's the first sign that you're in strange territory. And the relations are essentially the same, characterized by, well, the boundary of eta is 0. The boundary of, again, let's write a product of these symbols like this. This is equal to 0 if all the ui's are in O. And then the boundary, if you put the t first, sorry, U2 bar, you know, plus some multiplicative, you need more, you need some, plus a few other properties in order to characterize it, but it certainly satisfies these properties. Okay. Good. So it's at least well defined, and then you define the Milnor-Witt, so for X smooth, separated finite type, all the usual nonsense, over K. The sheaf is the unramified sheaf associated to this data. So, you use the same formula as for the Milner sheaf. You look at it at the generic points, and you look at it at the codimension 1 points, and you take the kernel of the boundary map.
Mark?
Yeah?
How do you see that this thing depends on T, given that the formulas are very similar to the previous?
Well, you try. You try replacing T with a T prime equals U times T. Let's just do it for, what's the boundary?
It's because of relation 2.
Yeah, it's because of relation 2. Let's see, right? If you take this is the boundary. I mean, it probably may use some of the properties that I had before that I omitted, but let's see what we need. Right? So see, you get a boundary here and you get a boundary there. So this will be 1, right? This goes to 1, this goes to 0, and this is, you can just, I left off, it's a derivation with respect to things which come from units on O and eta. Okay, that's the thing I left off. Didn't want to say it, but, and this thing goes, okay, you have to see how this commutes, but it'll be plus something. I think it'll commute with this. I mean, these two don't commute, but when you put the eta there, it'll commute. So you'll end up with eta times u, maybe with some other fudge factor there, but in any ways, that term won't be 0. Eta times u bar, sorry. Okay, so it does depend. Good point. Good. In any case, but what you can show is that the kernel doesn't depend on it. So you choose, in other words, you have to make a choice at each step of a parameter for each codimension 1 point, but it's still okay. Because you're just looking whether something is 0 or not, and that doesn't depend on anything. Okay, good. Glad you have your sheaf. And you also have a resolution, or maybe it's called a Rost-Schmidt resolution or Gersten type resolution. Which I'll get to later. Not there yet. Okay, but before we do that, I said this is a quadratic refinement. So what does this have to do with quadratic forms? So let's talk about that first. Okay, so the quadratic forms is by GW of F. F is our field. This is the Grothendieck-Witt ring of, so I'm going to be a little lazy here. I'll say of quadratic forms. So from now on, we're going to always assume that the characteristic is not equal to 2. For the characteristic equal to 2, the proper theory is you use symmetric bilinear forms, but I don't want to have to say that each time. So let's just ignore the characteristic equals 2 case. So what is this? You take the set of Q, which is a non-degenerate quadratic form, coefficients on F. Then you take up to isometry, in other words, up to change of variables, linear change of variables. And this thing is a monoid. You can take Q and you can take this direct sum with Q prime. So what is this? If Q, let's say, is a sum Qij xi xj, where this is some symmetric matrix, and this is then you can write this thing in terms of other variables. Then this is just the sum. You just have separate sets of variables. Okay. So this makes this into a monoid. It's commutative because when you switch the order, it's an isometry. And then you can group complete it. That's the Grothendieck construction. So you take, it's a commutative monoid, and then you take the universal abelian group that it maps to. Okay. So that's what this is, an additive structure. And then you also have this multiplication given by tensor product of quadratic forms. So again, so you have these symmetric matrices, I should have, and then if you have two matrices, you can take their tensor product matrix, and it'll again be symmetric, and that's what you get. So let me just mention that you know that every quadratic form is isometric to a diagonal form, right? And then if you take two diagonal forms, and then, for example, we write this as a notation just like this. These are the one-dimensional quadratic forms. So in other words, this guy, A, these will be non-zero elements in the field, and A is just the quadratic form, x goes to ax squared. And if you take A tensor B, or just A times B in the Grothendieck-Witt ring, this is just the one-dimensional quadratic form where it's the product of the coefficients. Okay, so that's the multiplication. That's the ring structure here. Good. Okay, and then you also have the Witt ring. You have a special element, H, which is just 1 plus minus 1. It's the hyperbolic form. And you have the Grothendieck-Witt ring, W of F. Obviously the Witt ring. And that's just the Grothendieck-Witt ring modulo the ideal generated by H. And it turns out, it's not hard to show, if you take any quadratic form times H, it's just a multiple of H. And which multiple is it? Well, this, if you think about it, so a quadratic form, non-degenerate, it has a rank. It's just the dimension of the vector space on which it's defined. And since you group complete, the rank becomes a homomorphism to the integers. And if you take a quadratic form and you multiply it by H, it just multiplies H by the rank of the quadratic form. So that just reduces to the one-dimensional case, because every quadratic form is a sum of one-dimensionals. And then it's a simple change of variables. Because, at least in characteristic not equal to 2, this is the form x squared minus y squared, which we all know is equivalent to the form x times y by a change of variables. And then if you multiply that by a, you can absorb the a into the x by a change of variables, and so it's again the same thing. Okay, so the h sort of absorbs all the multiplication. It's a funny element. Good. So that's the Witt ring, Grothendieck-Witt ring of a field. And what does this have to do with anything? Well, it's a theorem of Morel that this construction of the Milnor-Witt K-theory of a field puts together the Milner K-theory of the field with the Grothendieck-Witt and Witt rings in one convenient package. Good. Okay. So, so we can do the following thing for U, a unit. So what do we have? We have, first of all, we have this guy, the one-dimensional quadratic form in F, and we have an element which I'll, for reasons which you'll see, for the obvious reason, this is in K Milnor-Witt 0 of F, and it's defined to be the following gadget, 1 plus a to u. And notice that the relation 2 says that sending u to 1 plus a to u is multiplicative. In other words, it defines a homomorphism from F to the units in Milnor-Witt 0 of F. That's just this relation 2, if you think about it for a second. And in fact, it descends. We have this other homomorphism here to the Grothendieck-Witt group of F. And the theorem of Morel is that there's a homomorphism, let's call it phi, I don't know why, that it extends, and Morel's theorem is, so first of all, this extension phi is an isomorphism of rings. So this guy, sorry, right, it extends to this. Secondly, we have a similar map. We can send for any n less than 0, we can send u to eta to the minus n times this element u. That's this element u here. And this will be in Milnor-Witt minus n of F. And remember this relation 3, it said eta times h is 0. So this maps the Grothendieck-Witt group of F onto this guy here with kernel. So it maps here with kernel equal to the ideal generated by H. So it gives an isomorphism of the an additive isomorphism of this with this group. So it's actually an isomorphism of GW modules, right? This becomes a GW module via the multiplication from K0 and this homomorphism, and this by the ring surjection. So I'll just say isomorphism. No, eta to the n. N is negative. What did I do wrong? So n is negative, so I can take eta to a positive number. That makes sense. Eta has degree -1. So this lands for n negative minus n. Yeah?
Eta is in degree minus.
Then that's plus n. Sorry, yeah. Thank you. Good. Somebody's paying attention. Good. And let's see, what else? 3. What happens for n bigger than 0, or minus n less than 0? We have I of f is equal to the kernel, so the augmentation ideal. It's kernel of the rank map from the Grothendieck-Witt group of f to z. Then there is so of course, if you if you look at just the relations defining this thing, we can map this to the Milner K theory by sending, a symbol u1 up to un to this symbol and sending eta to 0. This gives, in other words, then the funny relation here becomes just the additivity relation here, and the Steinberg relation still the Steinberg relation. So that's a well-defined map, and it's obviously surjective, and it has kernel I of f to the n plus 1. This is a non-obvious fact. This relies on the Milner conjecture to show that that's really the kernel. But in any case, there it is. So the difference between the Milnor-Witt theory and the Milner theory is exactly this power of the augmentation ideal. Okay, so yeah, I'm rapidly running out of time. So I have to say, where's the orientation sheaf coming in? So I have to make one more definition. We have to look at the twisted Milnor-Witt sheaves. So we already have the Milnor-Witt sheaf as the unramified theory associated to the Milnor-Witt K theory of fields. And notice, via this map, if we have a unit in F, it gives us a unit in this ring. Right? This is actually in here. Its inverse is, since it's multiplicative, it's the pointy symbol on U inverse. So this is a unit in here. So for a field, you have an action of the multiplicative group of the field on this ring. And that extends to an action of, for units, the multiplicative group of units in a local ring into the stalk of the sheaf at that local ring. So I'll just say it this way. Sending u to multiplication by u gives an action of the sheaf. Let's say we're on a scheme OX star on this whole graded sheaf. Now, in other words, this sheaf, you can think of it this way, is a sheaf of modules for this kind of sheaf of group rings. Just so I can write down some funny tensor product. Now, if we have x, L over x, a line bundle, then we also have an action. So we can think of this thing as the sheaf of nowhere 0 sections. I'll just write it that way. And this, of course, is also a module for this guy. And we define the twisted Milnor-Witt sheaf. You just take the untwisted one, tensor it over ZGM with this L star. Okay, so one nice thing to note about this is so if you take the one-dimensional quadratic form for a square, of course you can absorb the square into the variable. This is isometric to the one-dimensional quadratic form with the unit. Or if I take u times v, this is the same as v. U squared times v is the same as v. So that says that if L is isomorphic to M tensor 2 for a line bundle, then the twisting doesn't do anything. So it's untwisted. Or I can even do this for an additional line bundle. Okay. So it only depends on the line bundle modulo squares.
Does that say that the ring of F is isomorphic to all the K?
Yes.
Okay.
Because, yeah. So multiplication, once you're in the negative range, multiplication by eta is an isomorphism. It's another way to say it. They're all isomorphic. So you have this funny quasi-periodicity. It's the various Milnor things until you get to the Grothendieck-Witt group. Then it becomes the Witt group, and then it just stays the Witt group. So if you like, another way to say it, if you take this sheaf of algebras and invert multiplication by eta, it's just the sheaf of Witt rings. Yeah, we're going to use that sometime later, but I'm really way behind. Okay, so what's the use of this? Well, there are two uses of it. Maybe say one use very briefly, which come in a little bit later. But I guess I can make my main definition now. Oops. Okay. So definition. So again, we're on an X smooth scheme over a field, Lx a line bundle. Then the Chow-Witt group with orientation L is by definition HP on X, Milnor-Witt P twisted by L. Okay. So what is this? This is sort of like cycles. This is cycles with coefficients in quadratic forms. So why is that? You look at this Gersten Rost, somebody tell me the correct name, resolution of Milnor-Witt P twisted by L. And in order, so we can actually make this independent of choices, the boundary maps independent of choice of parameter, you put the choice of parameter into the line bundle. So you twist the stage, the Milnor-Witt P, or let's say it would be P minus, say, J for something of codimension J of Kx. You twist by Ix upper star of L, that's already in there, and then tensor this with, let's call it the orientation sheaf at X, where what's this orientation sheaf at x? So you have x is the generic point of some variety on x, and you take the top wedge, which will be the jth wedge. X is going to be a codimension j point of the normal bundle of x closure, well, of x, let's say x in x, where this just means the top wedge, you take the maximal ideal of x mod its square and take its dual. So this gives you a complex, and at the end of the complex, so it starts out with this Milnor-Witt P twisted by L. Well, it's not at the end. Now if you're in codimension P, you have a term, it's B, let's take the global sections. You have the x and xp, and this will be the Milnor-Witt 0 of kx with a certain twist. It'll be twisted by ix upper star of L, tensor this orientation sheaf. And then you have a similar boundary map coming from Milnor-Witt. Sorry. Yeah. Yeah, exactly. That's where the t goes. Yeah, that's exactly where it goes. So it cancels out this dependence. Here you have a similar story. Let me not write it all down. Various orientation sheaves here. And then you have a continuous. So remember, this is some kind of a Grothendieck-Witt group with some twist. Twist in the orientation, and you have a boundary map to a similar sum of things in codimension p plus 1 of a Milnor-Witt minus 1 with a similar twist. And so it tells you that this Chow tilde p xl, maybe I call this thing, it's just call this delta p, and this delta p plus 1 is equal to the kernel of delta p modulo the image of delta p plus 1. And you can see at least the generators in here are you have a codimension p point and you have some kind of quadratic form on the residue field of that point. There are some extra conditions on the codimension 1 points along this subvariety, so those have to be satisfied in order to get something in the kernel. And then you mod out by some kind of divisor map coming from things in now a Milnor-Witt K1, which is no longer, it's a little more complicated than the residue field, of things of one dimension higher. Okay, so it has a cycle theoretic type description. Okay, so that's that. And let me finish off with a very brief, maybe I'll just make the statement and then I'll say more about it next time. So finally, we have relations to the motivic stable homotopy category. Since I'm out of time, I'll have to say more about this next time. But this thing, this SH of K, is a symmetric monoidal triangulated category. So the unit is the so-called sphere spectrum. And then when you have an object in here, it has homotopy sheaves. So every object, E, in SH of K has bigraded homotopy sheaves. I'll say more about how this comes about next time. Let me grade them like this, pi A of E, comma B. And the theorem of Morel, let me finish with that, puts this theorem is essentially why he defined these things. One good reason why he defined them. And then I'm done for today. Okay. Then, so theorem Morel. And I'll say a little bit more about how you get this map. I'll just say it now. There is a natural isomorphism, or there are natural isomorphisms from, if you view this Milnor-Witt sheaf in degree -n, this is now a sheaf on smooth varieties over K to this pi naught of the sphere spectrum in degree n. Okay, so I'll say a lot more about this next time. Thanks very much.
So is there any reason we choose the geo of nx and nx?
Yeah, not really, because as I mentioned, yeah, I mean, it's which one. If you take a square, it doesn't change anything, right? If you twist by a square, so the difference between a line bundle and its dual is the square of the line bundle. So in some sense, it's a matter of taste. But yeah, the orientation, you think of it as given by the normal bundle rather than the conormal bundle. So in some sense, you could equally well do it without the dual. Yeah. Some of the formulas later on come out better with the dual. Yeah.
And the
Yeah.
Witt group is a quotient of the Grothendieck-Witt group by the hyperbolic time?
Yes, that's right.
Okay.
Yeah. Yeah.
So what's the relation between these like Chow groups and the usual ones?
Yeah, well, you have this surjective map. Yeah, there's a surjective map, right, from the sheaves, and that gives you a surjective map, or not a surjective map, it gives you a map. So you have this map of sheaves. Actually, the twist by L, when you kill eta, right, remember this thing u was equal to 1 plus eta u. So when you kill eta, these things all go to 1. So the twists go away. And so for every L, you have this map here, which is just essentially sending eta to 0. And so this induces a map on the cohomology and you can see what it is if I still have the complex. In codimension P, you have a quadratic form at the generic point of your subvariety, and you take its rank. That gives you an integer. That's the associated cycle. And what happens on the K1 part, well, when you kill eta, it kills all the symbols except for the ones which don't involve eta. In other words, just this bracket, the square bracket u, and that goes to a non-zero function on your curve, and the divisor maps are compatible. So it sends it to the usual divisor of that function. So it gives that's another way to see what that map is. Yeah. Yeah.
For purposes of calibration, if you think of the usual maps of simplicial spheres into something, are those the pi star where the n equals 0?
Yeah, so the notation I'm using, if you have some general E here, this is the pre-sheaf associated to U goes to, you take A, it's the one which is the more natural one. You take A suspensions with respect to S1 and B suspensions with respect to GM into E. So right, exactly. This is the one where the topological part has degree 0. And it's a theorem of Morel that if you take the part of the sphere spectrum where the topological part is less than 0, those are all 0. It's a connectedness theorem. So these are analogous to the pi 0 of the stables pi 0 of the sphere spectrum, which we know is just Z. It's the first non-trivial answer, and you can see it's highly non-trivial compared to usual topology.
Okay, more questions? Seems not to be the case. Then before we thank Marc again, let me remind you that tonight at 7 there is the conference dinner at the Brauhaus Bench, and right next to the door you find instructions how to get there. So that should be easy. Okay.
Thanks very much.